Hello, everyone. My name is Sri. That is actually my full name that nobody except my mother uses. And this talk is Explain Plans and You. So, I want to disclaim by saying that here there may be no dragons, in that it is a very beginner level talk. It's not about something like a cool new feature that you guys might not have heard of. It is not about some new tool that I wrote. It is one of the first things that I think that relational databases came out with, which is explain plans. If you don't know what that is, then I really, really hope you get something out of this talk. The reason I'm giving this talk is because I assume that I can't be the only one who has had a non-traditional introduction to relational databases or database in general. I just showed up at my company and they were like, yeah, make this query faster. That's your first assignment. And I was like, okay. And the other thing is that explain plans, they kind of pop up. From experience, I've seen a lot more people who use the command line tools for SQL, like PSQL or something, be more familiar with this, because if you're using something like, I don't know, DataGrip or whatever the cool PG admin, right? It doesn't really show up unless you really, really go looking for it. So that's the other reason I thought people might not be very familiar. As for myself, I work at a $1 billion financial company downtown Chicago. I'm the principal software engineer there. My team owns a bunch of services and they work on really big databases. All that's telling you is that I might know something I'm talking about. That's all, might be worth listening to me. So I work at this company called Nova. We are a pretty big shop. We have about 150 engineers now. We're a public company. It is honestly a cool company to work for. I've been there 5 years. And the usual, you just reach out to me if you're interested, if you're in the Loop area in Chicago. And with that, let's get started. Gentle introduction, gentle being my version of gentle. I don't know if that's your version of gentle. The talk actually only is about 15 slides, and we are on slide number 5, right? So the point of this talk is for it to be very interactive. So the aim is kind of like education. So I really, really wish that if you guys have a question, please stop me and ask the question. I'm not doing the hold your questions till the end thing because, yeah, I don't want to lose anyone along the way. So if you have a question, please stop and ask, yeah? All right, so first of all, why should you care and when should you care? So first, remember that Postgres, how many people know that Postgres runs a cost-based optimizer? Okay, so I'm going to explain what a cost-based optimizer is really quick. Right? So a cost-based optimizer is when you put your query into Postgres, it goes through a bunch of steps, right? It goes through parsing, lexing. I don't think it goes through linking, but basically the engine is taking your query and it's okay, what does this person want to do? First of all, is this query even legit? If you just did select semicolon, the lexer is going to be that's not a valid statement, right? Or if you did select one fro table A, right? It'd be yeah, what fro, right? So that's lexing, right? It's checking your syntax, checking you got or let's say you select one from a table that doesn't exist, right? And it's yeah, I don't know what that table is. So that's level 1. So it's lexing. Then it's parsing, right? Parsing is where it's finding the things that you wanted to do, which tables you wanted to join, blah blah blah. And then ultimately it goes through query planning, which is where the engine inside Postgres that's going to execute your query is going to come up with kind of a game plan of how it's going to run that query, right? But to do that, it needs to make a decision because the engine has the same aim as you, which is it wants you to get out the door ASAP, right? It wants to sit around doing nothing. So it's okay, what's the fastest way I can get this person out of my system, right? And so it uses statistics to derive that answer. So there isn't only one plan. It actually makes a bouquet of plans. So it's how are all the ways I could get this person the data they want, right? And starts just enumerating them. It's well, I could just read through the entire table. That's an option, right? I could use an index if there is an index. That's an option, right? So on and so forth. And it's if you have to make a join, we'll see all the different join strategies. But it basically lists all the possible ways it can get you your data, right? Then it assigns a cost value to each one of those, right? So it's yeah, well, if I had to sequentially scan this table, it would take me X. If I had to do this, it would take me Y. And then it weighs all those costs and then picks the lowest cost, and then that is the plan that it ends up executing, right? So it's kind of like, does a play-by-play, right? And the lowest cost plan ends up winning. Now, it might be worth noting that the lowest cost plan may not be the best one if certain parameters change. But that is plan stability, which is something that we're not going to be covering in this topic, but it's a really interesting topic. But the way it costs those plans is using statistics, right? So where does it get the statistics from? It's actually, I'm going to do this a lot, but I'm going to be dipping in and out of the presentation. But have you guys ever done this? Some people have, right? Have you seen there's a thing running there called the stats collector process, right? That's one of the many things that runs. That's the guy collecting all the stats, right? So that guy is basically just sitting in the background. It's a process completely outside Postgres, right? Like it's still under the Postgres postmaster, right? But it's just completely separate, just sitting there. All it's doing, every time you're inserting, updating, deleting data, right, it's sampling it and collecting some statistics on what your data looks like, right? And those are the statistics that the planner uses to cost the plans and then pick the winning one. With me so far? Okay, that's why Postgres is a cost-based optimizer, right? That's why you don't have to be like, hey, Postgres, by the way, I think you should use an index. Postgres is like, okay, I know. So that's why Postgres is a cost-based optimizer. And how do you know what Postgres is going to do? That's exactly what explain plans tell you. Right, so that's what we're going to cover in this talk. So we can't control the optimizer, and that's like an important thing that a lot of people who are coming from like other databases, at least they used to, kind of like trip over, which is, what do you mean I can't tell the optimizer what to do? I'm like, no, you can't. It's all just math, right? So and for good reason, right? Like the Postgres optimizer is one of the smartest pieces of code that exists in the industry, right? Like it's written with a lot of experience. It gets smarter every year. Like I'm sure if you go to like Magnus or somebody else's talk this year where they're talking about Postgres 12, one of the line items is going to be, yeah, Postgres just got faster, and you don't have to do anything about it. It's just faster, right? And that's because they make the optimizer better. They take experience and they shove it in there. So like, just think about the fact that if you want to go against like 20 years of experience, that's impressive. So, and a final thing to keep in mind is that when optimizing, right, like when you're writing your query, right, you're always the guy writing the query for the first time, right? And then you're also going to be like a guy who leaves the shop like 3 years later. And so when the poor woman comes in after you and she's like, oh my God, what is this, right? Like it takes like 5 hours to run. It was great when you wrote it, right? But things changed since then. Right? Because data is kind of like a living thing. Maybe you were doing a lot of business in Texas, and now you're just out of Texas, and you're most of your business in, I don't know, Idaho, right? So what is fast today may not be fast tomorrow, and the way you kind of foresee that is by looking at the explain plans, and you're like, well, it's using this index, and this index has this kind of like cardinality over this set, and do I foresee that changing, right? And like just having that forethought helps a lot. So how do I do it? It's actually very simple. You can do it right now if you have Postgres running on your computer. Just take a query. Just literally, if you take select one and then put explain in front of it, it'll tell you how it's going to execute select one, right? And you know what? I actually don't know what the explain plan for select one looks like, so I want to try it. Okay, there you go. So that's the explain plan for select one. It's like, yeah, I'm going to give it to you. That's how I'm going to execute this. There's no table scan, there's no index. You wanted one, here's the result, right? It cost me nothing, and you wanted a row. The width was 4, that's 4 bytes, it's an integer, right? And it's like, yeah, it's 1, right? And that's actually the best way to start, because you kind of have an idea of what it should look like, right? Like if this had come back with like, oh yeah, I went through like 4 tables, you'd be like, what? Why did you go through 4 tables to give me back a 1, right? So makes sense. Right? So that's actually just how you do it. You just explain, and then you do the query, and then it shows up. That's great. So explain explains the plan or the play the optimizer thinks it's going to run. And then there's explain analyze, which actually ends up running the query. Now, that's really important to remember. So there are actually 2 versions of explain. There's explain, and there's explain analyze. Right? And explain analyze actually runs the query. And I can't stress that enough, because if you explain analyze a delete statement, It's not just like, oh yeah, I think this is what I'm going to be. It's already deleted it, right? So just keep that in mind. So if you want to like explain analyze, just keep in mind it actually affects the statement. So if you want to try it out, you might want to put that in a transaction and roll it back, right? So why the two things? Why the difference? Remember, Postgres is a cost-based optimizer. So explain is based on estimates, right? The optimizer is like, well, I think there are 100 rows in that table where the state is Texas, I think, right? Because that's what the stats collector has collected so far. But when you end up running the query, the optimizer could be wildly off, right? It could be like, oh yeah, there were like 10,000, you were wrong, right? And the reason for that, we're not going to cover in this session, is because of operations that you're performing on that table and how your data is being sampled. Remember, it's just sampling at the back, right? So you have gotten really unlucky, right? Your stats may not have been updated. If you just literally ran a delete statement and the stats collector hasn't had a chance to update all the stats, right? It just believes in the old stats, right? So the difference between explain and explain analyze is you get to check how accurate the estimator was, right? Like how accurate the optimizer was when it was thinking that, nah, there's really just 10 rows here from Texas, right?
I was just going to say, it's good to note, too, that, like you said with the delete, but if you have a query that takes an hour to run or something,
yeah,
you're going to be waiting for an hour.
Oh, exactly. Yep, that's true. It's actually running the query, right? The only difference between explain and explain analyze is explain is, I think I'm going to run it this way, and explain analyze is, I ended up running it this way, right? Both of them produce the same plan. It's just that one of them is projections and one of them is retrospection, right? So worth keeping that in mind. Thank you for calling that out. OK, so what does an explain plan look like? I kind of already cheated by showing you. But here's an example of an explain plan. Trust me, this is like a pretty nice, easy one, actually. They get really gnarly. But that's the whole point of the stock, which is when I look at this, how do I like not panic, right? So the cool thing, the first thing, if you see the explain plan, any explain plan has a structure. It has a shape, right? So you look at this and you see that, oh yeah, it's kind of like it's going deeper and then deeper and then deeper, and then it kind of comes out and out and out. And that's because it's just a big old stack, right? Like it's stack upon stack of operation. And ultimately, the heart, the innermost operation, right, is the first thing that gets run, and then it kind of feeds up. Does that make sense? Right? OK, so there are like 6 terminologies associated with the explain plan. So every one of the pointy arrows, right, a pointy arrow is a node, right? So like what's happening in the step? So that node says hash join, right? And that's what it's doing, is hash joining. And then whatever it ends up producing, it gives to its parent. It just bubbles it up, right? And so the output of the child goes up to the parent, right? So that's a node. So I don't know if that's very visible, but it says bitmap heap scan on loan applications LA. That's a relation. So loan applications is a table in this case, and it's telling me that, oh yeah, I scanned loan applications. By the way, you also aliased it to LA, so it's kind of like nice that way, right? It's like, what is this happening on? What relation is this happening on? Is this happening on a table, or is this happening on a child giving me data back, right? So relation. Cost. And this first keyword is so important. Relatively, how expensive is this step? Right? And the reason that's so important is because if you came to anyone and you were like, yeah, that step cost 400, I'd be like, well, what am I supposed to do? Yeah, OK, it cost 400. 400 has no meaning, right? There is no unit for cost in Postgres, right? It's all relative. Yeah, if you come back to me like, that step cost 400 and every other step cost 1, and I'm like, maybe we should look at that, right? But if you just came and said 400, it has no meaning, right? And I'll tell you in a second how the cost is calculated. There's the modifier. So the modifier is kind of like, so in this case, you can, let's see, where's the modifier coming from? Sheesh, sorry. Yeah, so you can see it says recheck condition. So this thing right here, recheck condition, right? So modifier is kind of like may modify the result of the child before handing it off to the top, right? So like, for example, there's a sort here. You can have like examples of other modifiers might be like filters, etc. So modifiers kind of take the result of the child and do something to it, may not even mutate it. Like in this case, it's just a recheck, right? And kind of talking about why there needs to be a recheck is like a whole different talk, right? But yeah, it's just kind of making sure. It's kind of making sure that really there are no rows in there that don't have that condition or whatever. And then it hands it off to the parent. Then there is rows. These two are very simple. So all the way to the right, if you see there's rows, that is how many rows will be returned by this node, right? So in this case, 2 rows will be returned by that node. Solid. And then there is loops, which is how many times will this step be executed. So like in this case, the loops is 1, so it is going to return 2 rows once, so it's just 2 rows, right? If the loops was, let's say, 10, right, then it would, that node will occur 10 times. And does anyone want to take a guess at when is the most common time you would see a loop? A cursor? Oh, yeah, maybe, but yeah, we're not doing cursors here. And also, you can't do cursors inside queries very easily. Table scan wouldn't loop. It would just be one scan. Subselects, right? From, and then you have a correlated subquery. Yeah, I think it's going to loop. It's like, oh, yeah, once for this, once for this, once for this. Nested loop joins, right? It's right in the word, right? So, yeah, so loops are when it's going to execute the same thing over and over and over again, right? So these are 6 terminologies. Node, relation, cost, modifier, rows, and loops, right? You know what's the best part of an explain plan? You can regenerate the entire query from it, right? Like if you didn't give me the query and you gave me an explain plan, I can kind of guess, outside of what you selected, I can kind of guess what you were doing, right? And we're going to take a shot at that with this example, right? So again, remember, we have no idea what this query is, right? But the first thing you want to do is you want to go to the heart of the explain plan, right? Go as deep as possible. You're like, no, right? That's as deep as it goes, right? And you're like, it's like a bitmap or and a bitmap index scan and some other bitmap index scan. But it kind of, and we don't know what that is yet, but it's kind of given away in this recheck condition, right? And that recheck condition says where the account ID is any of 7812011 or some other thing is any of some null integer or something, right? What does that look like to you guys? It's a where clause, right? Exactly. So even easier than that, there's a word that says hash join. I'm going to go out on a limb here and say that's a join, right? So that's a join, right? And sorry, the next thing, as guessed correctly, was a where clause, right? OK, there's a sort operation. What do you think the sort operation is doing? Or by, exactly. And then there's a unique operation. What do you think unique's doing? Distinct, right? Bam. And that is exactly the query, right? Select distinct on from loan applications, join, where, or order by. Isn't that cool, right? That's why explain plans are so cool, because if you came to me with a query, right, and this is the thing that always trips me up, because like you kind of get experience with databases, and then people come to you and they're like, what's wrong with this query? And I'm like, I don't know, we'll have to explain it, right? And that's the beauty of Postgres, right? It's like, I have nothing inside me that you don't, right? Like, you have a computer with Postgres, I have a computer with Postgres, right? And we go to the database, and we're going to both explain it. The big difference between me and you is that I know how to read the plan, right? That's it, right? So there is no point looking at this query, right, and trying to guess what's going to happen, because I assure you that you're probably going to be wrong, right? And think about why. This is the reason we have databases, right? Because the database is collecting statistics, right? If you looked at this and you're like, I really think you should use an index, right? The database is going like, yeah, well, if I did, it would be like 10 times as expensive as scanning the table. Do you really want me to? And you're like, yeah, I didn't know that. And you're like, yeah, well, that's why you're not a database, right? So that's the whole point, right? Like, that's why the best part of explain is that you don't need to remember or like keep in mind anything. It's all there on paper for you, right? Because remember, your data is a living, breathing thing, right? So what is slow today or fast today might be slow tomorrow, right? So that's roughly the negative of an explain plan. And so we're going to do some experiments soon. But a word on costs. So costs are all a relative, right? It has no meaning, and I kind of alluded to this before, right? Like it means nothing, right? Like it's like, yeah, in fact, we can go take a look at the explain plan before, right? So if you look at this explain plan, it's like, yeah, there is like cost is 10.66 to 22.65. You're like, okay. But there is something interesting to note here, right, about costs. In fact, there are two interesting things to note. First of all, it's not a single number, right? The cost isn't 10, right? It was 10.662 something, right? What do you think that is? Like usually when you have a range, if anything, what happens?
First number is a startup.
Yeah. So it's a pipeline, right? Like Postgres, really smart thing, right? So it's not going to wait to produce the entire set if it can do something with the first member of that set as soon as it's produced, right? So it's just like, I got the first one, and the guy on top's like, I'll take it, right? And he's like, all right, here you go, right? And just keeps doing that, right? It's just shoving things up instead of waiting to get the whole thing and pass it off, right? So the cost is actually being pipelined. So you can see here, so it's like a hash join, and it's like, yeah, I'm going to like start joining stuff, and I'm also going to start giving it to you as soon as I start producing it, right? Now, next to that, there is a word that says actual time. That is actually time, right? Like that is actually believable, right? So when it says actual time is 0.048 to 0.052, right? It's, I believe, that many milliseconds? Yeah, it's that many milliseconds. So it's like, which is pretty fast. This is like 52 microseconds. So it's like, no. Yeah, 52 microseconds. So, so it's like, yeah, it took me about that much time from there to finish executing that node, right? That stabby lambda, that like pokey thing. Right? It took me that long, right? Here's another, so that's the first interesting thing to note about costs. They have ranges, right? And there's an accompanying thing that says actual time, which is actually time, right? So if you look through your plan and you find something that's like, yeah, that thing took 20 seconds and my query took 21 seconds, might be worth starting there, right? Because that thing took 20 seconds. That's most of your query, right? So if there's one node which took 20 seconds of your time and your query took 21 seconds to run and you want to make it faster, it's a good place to start. Because knock off the 20 seconds and there's only 1 second left, right? Second important thing about costs, they accumulate, right? From the heart to the top, they will only increase. Remember, this is a stack, right? So if the thing inside took 10 seconds to run, the thing outside cannot take less than 10 seconds to run because the thing outside can't do its job without the thing inside finishing, right? And that's, we can actually see that in this, right? So here there's a cost of 0.00 to 4.62. The moment you see cost of 0.00, you don't care about the number, but you look at that and you're like, that's got to be the heart of the plan. Because if the cost is 0, that's the first thing that's running, right? Because it doesn't depend on anything else, so it starts there, right? So, excuse me. So if you look at this, there are two 0.00s, right? Which means that these two nodes happen in parallel, right? That's why they're kind of sitting next to each other, right? And see, both their costs start at 0.00, right? So those two things are where the the execution of this query is starting, right? So they both run, and they both take slightly different times to finish, right? And once they're done, they give their output to this guy up here, this bitmap OR, right? And you can see that the bitmap OR started at 0.016 and finished, sorry, the cost was 9.21 to 9.21, and then it started at 0.016 and finished at 0.016. So again, come down here. The cost 4.62 and 4.60, and then look at the actual time, 0.014, and then this started and finished at 0.016. Are you with me? Sorry, I think I don't know if I did a good job of that. Again, 0.014, 0.001, whatever. And then this one started at 0.016. Why? Because he couldn't have started doing his job until both the children had finished. And if you look at the two children, the greater of those two is 0.014, right? And so he started at 0.016 because he needed both those outputs, right? So even though the data was being pipelined, since it had to do an OR, it had to wait for all the data, So it only started executing at 0.016 and kind of finished at the same time because computers, right? But yeah, cumulative. Sorry, go ahead.
Explain plan, I mean, when you do the explain plan, you are not running that query. You are just, I mean, the Postgres is looking at the query and giving us something, how it is going to do in the future.
That is correct.
So where exactly these timings come into picture, like actual timings and all?
This is an explain analyze.
Okay, so explain.
Yeah, so here.
That part probably, but
Yeah, sorry, yeah,
actual execution of the query?
yes, you're absolutely right. In fact, I'm going to do it right now. So thank you for calling that out. Oh, sorry, I need to exit this one second. Yeah, so let's look at that. That's a great point. Explain, it has cost, but it has no actual time, right? Because it didn't run the query. But if I just modified this to, now there's an actual time, because it actually ran the query, right? So explain analyze actually runs the query. I can't stress this enough. If you go and run this on your production system and you lock it up or you delete some data, I'm disclaiming all responsibility right now. I'm telling you again and again, explain analyze runs the query, actually executes it. All you're saying is, okay, now that you ran it, tell me really how you ran it and how long it took, right? So that's the difference. So, and you can, like, obviously here you can't see much difference because you're selecting one, right? But if there is a discrepancy, that is going to be because of stats being approximate or lagging operations on the database. And we're going to see examples of that.
So if I have like a problematic query which is running for minutes,
Yep.
more than that,
Yep.
it will actually run for
Yep.
long, like,
Exactly.
and I have to be careful.
Yep.
EMLs also whenever I
Precisely. So you have a couple of options, right? So you can explain the query. And in most cases, with good database administration, your costs are not very different from your actual, or your estimates are not very different from your actual costs. And that's a whole art, right? That's why DBA is still a job, right? And that's why it's important to have somebody who understands what the data in your database is instead of a machine. Machines are getting really good at this, right? But it's kind of cool when your database administrator is like, no, trust me, you're going to want to load that thing into memory on startup, right? And you're like, I don't believe that. He's like, no. It's like Postgres, like, I don't know. It's like database admins, like, no, man, trust me. You want to do that, right? And that's the edge. That's the human edge, right? Just to know that, like, no, I've seen these access patterns before. I have this history that you don't have, right? And I think that you should load this. So administrators have this ability to, like, control a lot of things in the Postgres conf file. So I'll show you what that looks like. Oh man. Shit. Hold on. Oh yeah, that's right. Okay. How many people have seen this file before? Okay, so that's the Postgres configuration file. A lot of things in here, like I'll give you simple examples. The number of maximum connections that you can open to your database is in here, right? The port your database runs in. Everyone thinks Postgres runs on 5432. Yeah, most of the time, right? But you can, if you're running a proxy or something, you might want to run on that different port. I don't know if you're like, just try to make your life difficult for no reason, you can run on a different port, right? But yeah, so there's like a bunch of configurations in here, right? One of the configurations, I forgot what the name of that configuration is, but there is a configuration parameter in here which tells Postgres how often to sample. Man, I forgot the name. There is a parameter best part of Postgres, it's all documented. So you just go to Google and you're like, sampling parameter Postgres, it's going to show up. And that thing dictates the discretization of your analog sample, right? So it's like, if you have like a stream of data and you're going to like sample that every once in n, that thing dictates it. Okay, so I'm going to come back to this file, so I'm going to leave this open for a second. But I hope that explains. Sorry, go ahead.
Just one question on
Yes.
analyze.
Yes.
If you have the actual time it took the node to run, why is time reported as a range?
Why? Indeed. Same thing. Because there is pipelining, right? So it's saying that I started producing results at this point, and I stopped producing results at this point. So in this case, it says actual time 0.013, because it started and stopped at the same time, right? But if you had a node that was feeding up, the same pipelining argument holds, right? Which is, I started producing results at 0.013, and I stopped at 0. Now, the parent may not actually use that pipelining. The parent might just be like, yeah, I need all the data to finish, so thank you very much, but just be done, right? But some parents actually make use of the pipelining, right? So it kind of, that's the reason, right? Yeah, but same argument. Okay, so, all right, so, yeah, blah, blah, blah. So, talked about costs. Oh, and this is a good time to, yeah. So where does the cost number come from? I mean, it's kind of nonsensical, right? Like 400, 20, 16. But where does it actually come from? Anyone want to take this? Yes, but is it all?
It's just a formula.
It is a formula. And CPU cycles is one of the things in that formula. You do set it in your config. All of these are true. OK, let's take a look at it. Here, this is your config file, right? And here, there's very nicely a section that says query tuning, right? And you look under that, and first you see planner method configuration, right? And it's saying it has a bunch of configurations like, should I bitmap scan? Should I hash aggregate? Should I hash join? Should I index? Should I index only scan? Should I materialize? Should I merge join? Should I nested loop join? Should I sequential scan? Should I sort, right? I actually don't know what TID scan is. I think it's tuple ID scanning, but I've never seen it. But those are all the operations that your planner can actually perform. So literally, the most complex plan in this world is comprised of a series of all of those operations. That's all it can do, right? It's just going to do them in different hours, different speed, different cost. But how is it going to come up with a cost? It's a formula with CPU cycles that you set. All true right here, right? So it says sequential page cost, right? Measured on, and that's the first thing that they say, measured on an arbitrary scale. There is no scale, right? They're just like, you know what? I think sequential page cost should be 1. It doesn't matter. You know, like, I know a lot of people do agile these days, right? But they're always like, oh, when you're like story pointing, right? You're like, how many points is this story? I'm like, I don't know. They're like, don't worry about it. Compared to the previous one, how many points is it? I'm like, yeah, but how do you know the previous one's right? You don't, right? So it's just all relative, right? Yeah, at the end of it, it doesn't matter. Anyway, so that they just picked 1, right? They were like, okay, you know what? The first one's 1. Based on that, random paging cost is 4 times as expensive. That's all it says. It doesn't say 4.0. It means 4 times 1.0, right? CPU tuple cost, which is what's the cost of, I think, materializing a single tuple. What is the CPU cost of materializing a single tuple? It's like, it is 1/100th of a sequential scan, right? And you can change it, right? So you can go in here and screw around with this. You can be like, what if sequential scans were really cheap, right? And Postgres will be like, OK, if that's what you want. But there's good reason to do that. That's why you need database administrators, because database administrators understand the hardware you're running on, right? So hardware changes a lot of these things, right? Because what is 1 on, let's say, disk at 15,000 RPM may not be 1 on SSD, right? So a lot of these, like, for example, random paging costs on SSDs are really low, right? You can, like, pick 1 page real fast, right? But there is something to be said for metal that is spinning at 15,000 RPM, right? You can scan metal really quickly, right? Especially if your disks are striped. So there's like a whole art to setting these things, which is tightly coupled with the hardware that you're running on, right? But the formula that uses things like CPU cycles based on costs that you set in here is actually published somewhere that I don't know, right? But that's how Postgres comes up with a cost for anything, right? And that's why those costs don't mean anything, because they're founded on things that don't mean anything, right? It's all relative, right? It's all arbitrary scale. So that's all about costs. But again, so since it's relative, you can compare costs, right, to find out which one should be optimized. Because if like most costs are 1 and there's like a 4,000, you want to look at 4,000, right? Okay, now we're going to do some live experiments, right? Because why not? I have Postgres running on my local computer. And so I have this test set up. It's a very simple test. There are 2 tables. There is a table called hashes, which is kind of like a lookup table. It has 5 rows in it. And then there is a table called hash test, which has a functional dependency on hashes. So hash test has a hash ID, which references hashes. It has a primary key. And then it has a code, which is like a bunch of random text that got hashed into a hash, which is the hash computation using that algorithm of that text. I didn't actually do the algorithm, right? I just like came up with some numbers. But the important thing here is the way the test is set up, they kind of collide. The hashes are all collidey, right? They're actually called that. They're collidey, bumpy, coercy. Like they're all hashes that want to collide. It's not a good hash function. It's not a hash function that has a collision of 1 in like 2 power 32 or something. It's a hash function that has a collision of 1 in 5, right? Because there are 5 hashes, right? So in other words, the data in this table in hash test is split 5 ways across the 5 hashes. So I have 13 million rows in hash test. So the number of distinct hashes is 13 million times 5 because they're only hashed 5 ways. Does that make sense? Right? And you'll see why I kind of set it up this way. Okay, so this is kind of, I could skip this slide based on whether people are familiar with it or not. How many people are familiar with like big O notation and complexity? Oh man, okay. I don't know how far we're going to get on this, but I think this is very important to know anyway, so we're going to do this, right? Because if you walk away from this and you're like, this guy taught me complexity, I'd be so proud. So complexities. So you walk around and people are like, oh yeah, that's O of 1, that's O of n, that's O of log n, O of n log n, right? And you're like, what? And yeah, so we're going to talk about why it is that way. So complexities, the big O notation is kind of a shorthand for the rate of growth of your algorithm with the increase of n, right? So if n, let's say, was ranging from 1 to 10, and your algorithm did not increase or decrease in speed when I change n, it's independent of n. It's constant, right? And that's the first example. So all of these have been depicted by a language that doesn't exist. I think I wrote Ruby and Go at the same time. But all of them run loops, right? And so we're talking about complexities all in terms of loops. Loops, I'm assuming people are familiar with loops, right? OK. So the first one takes n as an argument, and then it ranges over numbers from 1 to 100. So if I passed n in as 1 or 1 million, it is going to print out or do something that costs 1, again, 1 being relative, exactly 100 times. It doesn't matter what n is. It's independent of n, right? That is constant time, right? It is independent of n. That is, it runs in constant time no matter what n is. The second one is logarithmic, right? This one's a little bit more complicated. So if I pass in n, the loop starts at 1, goes up till n. So you can see instantly there is now a dependency on n, right? So whatever the runtime of this algorithm is, it depends on n, but the steps that I'm making grow by a factor of 3 every iteration. So the first time I'm 1, then I'm 3, then I'm 9, then I'm 27, right? So if I passed in an n of 1, I'll run once. Passed in an n of 2, still ran once. Passed in an n of 3, I ran twice. 4, twice. 5, twice. 6, twice. 7, twice. 8, twice. 9, thrice. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 26, thrice. 27, I ran the 4th time, right? So you can see that it's taking more and more n for me to run one more time. So the growth there is logarithmic, right? And I can write a formula and prove that to you, right? And in fact, I will, but logarithmic. So based on the growth of n, I only run logarithmically as many times. The next is the most standard algorithm, linear time. I'm going to go from 1 to n. So if I increase n by 10, I'm going to run 10 more times. If I increase my n by 100, I run 100 more times. Linear. Polynomial. I am looping over n times. Right? So I open a loop. So for the first iteration of the outer loop, I run the inner loop n times. And for each iteration of the inner loop, I run another inner loop n times. So I do it n into n into n cubed times, right? So if I pass in an n of 1, I'm going to do it once. But if I pass in an n of 10, I'm going to do 10 into 10 into 10. That's 1,000 times. So it's growing as n grows by a factor of n cubed. Polynomial, right? Squares, cubes, quadratic, like power 4, 5, all polynomial. I'm missing one in between, which is factorial, and that's just it's a whole thing. I'm not going to go into that. And then there is exponential time, right? Which is, if you give me n, I'm going to go 2 power n. So if you give me n of 1, I'm going to go twice. But if you give me n of 10, I'm going to go 2 power 10 times, right? And 2 power 10 is a very large number, right? So by increasing n, you're increasing the number of times I run exponentially, right? Exponential time. So this doesn't talk about big O. It's just told you what the dependencies on n are. So what is big O? The O off, right? By the way, it's big O off, but we just say O off. Here is another set of examples that are slightly different, but they're in the same class. So let's take the first one. So the first one, constant time. Both of those are constant time. And you're going to look at that and be like, what? Like the second one goes, I don't even know what that number is. But it goes from 1 to like a very large number. And the first one just went to 100. How are they both in the same class? Because neither of them depends on n. Right? So even though fundamentally the costs are different, they have the same rate of growth of cost, which is independent of n. In both cases, if I pass in n, they're going to run a constant time independent of n. And so they're in the same class, noted by big O. Right? So it's big O of a constant, thus becoming big O of 1. And the constant doesn't matter. Right? So it's constant time. The second one, logarithmic. Right? So you can see on the left-hand side, it grows by 3. On the right-hand side, it's growing by 2. Right? So the number of times they're going to execute fundamentally is going to be different. But the rate at which they're growing when I change n is similar. Right? Not the same, but it's similar. When you plot the curves, they're going to look kind of the same. They're going to grow the same. One is always going to be more than the other. But that's not the point. The point is they're going to grow the same way. Right? They both depend on n the same way, which is if you increase n, they will only increase so many times because they're logarithmic, thus becoming logarithmic. Right? The formula there actually derives, just don't worry about it. I just wrote it for myself. I had to prove it. The next one is linear. So you can see that in the second case, I am looping over John. So first one is 1 to n. The second one is 1 to like a gajillion times n. It doesn't matter. Because if I increase n, they both grow at the same rate. The second one, of course, for the same n, will run a lot many more times than the first one. But if I increased n by 1, the number of times it increases grows at the same rate as the first one. Right? Still much more, still 1 gajillion more, right? But it's not 1 gajillion square more or 1 gajillion cube more. It's just 1 gajillion more, right? And the first one went up by 1, right? Both grow at the same rate as n, thus becoming O of n, right? Just dependent on n, right? The next one is polynomial time, similarly becoming O of n cubed. And the final one is exponential, becoming O of 2 power n. Does that make sense? Great. OK. All right, indices. Indices are good. You want them. They have a cost, right? That is, an index is a full replica of the data in your table. So when you index a column, that's a whole thing. It's a relation. The index is a separate copy. It's not free, right? Which means, and again, remember, space doesn't cost anything. So we're not worried about space. We're worried about CPU cost, right? The actual execution cost. Anytime you insert or update or delete, you have to maintain a second thing now. If you want to use the second thing as an index, right, If somebody moves out of one house and goes into another house, you want to maintain the address dictionary, otherwise your address dictionary is useless, right? Which makes the cost of moving a little bit more expensive because you got to maintain the dictionary. If there are 10 dictionaries, you got to maintain 10 dictionaries, right? So an index is kind of like that. It's a dictionary, right? So there's a cost to maintaining it, but generally it's good. You don't have to worry too much about that cost. It does slow down your operations, but it's worth it because it makes your read operations really fast, right? So that's a decision that you make most of the times without even thinking that, yeah, I want my reads to be fast because I don't do that much writing. But if you are predominantly writing and reading like once every 15 days, you might really want to think whether you need an index, right? All right. So an index scan node kind of looks like that. It'll just say index scan. Pretty straightforward, right? It's like, yeah, I scanned an index. Easy, right? The opposite of this, kind of opposite, is a sequential scan. That's when the guy, the planner is like, I'm going to scan your entire table, right? So if, and this part's really important, if by your estimates, your query should run faster, it might be worth looking for a node like this. I'm not saying that, oh my God, that's the worst, you got to get rid of it. In most cases, if you're like, look, I have a table. I think the table has a primary key. Table has 1,000,000 rows. I want where ID equals 1. And your planner is like, I'm going to sequentially scan it. You're going to be like, really? To get me one column, you're going to sequentially scan 1,000,000 rows? You got to look for this, right? But there are cases where you don't, like it's actually better to sequentially scan, right? And I am going to see, yeah, OK. So I'm actually going to skip joins. And here are sequential scans. They're usually bad, right? But there are actually 3 caveats to that. First one, you need all the data from the table anyway. What index are you going to use? You need all the data. You got to scan the table. It doesn't matter, right? In fact, if you used an index, it's going to be slower because you were just like, I'm going to go over every row in this block. But let me look up the address for the first one. You know it's right there. Just walk it, right? So yeah, when you want all the data, you sequentially scan. And the second one, you need so much data. You don't want all the data, but you need so much data that indices are just an overhead. This is when looking up addresses, while it seems smart, is actually slower because Postgres can spin disk fast, right? So the rule of thumb is, if you're getting more than 8% of the data out of your table, Postgres is just going to be like, yeah, if I have to do index lookup for more than 9% of the data, it's just faster to spin the disk and read through the table and then filter it out, right? So you're reading so much data. That's when the cardinality of your predicate, your where clause, is not high enough. Sorry, it's not low enough that you're scanning too much. You're like, where state is Texas, right? And yeah, 90% of my business is in Texas, right? I could use an index, but it's 90% of my data, right? The final one is your table is so small that you don't need an index. You got 10 entries in that table. You don't need an index. You can just ask each one of them, are you, you're not, right? There's only 10 calls you need to make, right? So 3 cases where sequential scans aren't the worst, and you probably don't want to optimize those, right? But normally, index is pretty solid, right? You kind of want those. I had a whole thing about joins, which we're not going to get to, but I'm really glad we covered complexities instead. I think I have a minute left. I'm going to just pause for any last minute questions you guys might have. And then, of course, I'll post this. And then there are little snippets of code that you can run yourself. And then remember, the setup kind of tells you how to set up the data. I can even upload the script. It's 4 SQL statements to create that data. So any questions I can answer? Yeah, there's it gets uploaded. There's a on the Postgres website, on the conference website, or I think it's actually on PostgresUL.
It's going to be on the PostgresUL site. We're going to be tweeting out about where to find the slides after the conference ends. Here's where you go for all the slides.
The slides or the video?
The slides are going to be on that, and I will tweet about it. So just please follow our social media account. We'll publish that on email as well. And then in terms of the videos, those will be uploaded probably next month, and there will be videos of all the sessions, including closed captioning.
Cool. And I'm just going to repeat what Sarah said. They're going to tweet out where the slides go, and there will be videos posted by next month. Yeah. So you'll get the slides. Any other questions? I don't know. I don't even have time. Last question.
I mean, there is a copy break after this.
Oh yeah, there is a coffee. Yeah, if you really, really want to sit around and listen to me talk about Postgres and not drink coffee, you're welcome. But last question before I sign off? No? No? All good? Excellent. Thank you for coming. Hope you learned something.